Hi guys, this is my black hole lab presentation. First, it is important to note that the purpose of this lab has two parts. The first part of the lab focuses on the net force acting on the star at all data points and then utilizing this information to estimate the mass of the black hole. It is important to note in part one, the star is the system and the black hole is the surroundings. This information is extremely important when it comes to the gravitational force equation. The time between the first and last data point is 1 day, or 86,400 seconds. For part two, we are asked to determine the initial velocity of our spacecraft when it launches from the planet. The catch here is that we need an initial velocity that would allow the spacecraft to get close to the black hole without being sucked in. In this scenario, the spacecraft is the system, and the black hole and planet are the surroundings. On the other half of the slide, I've listed the fundamental theorems that were used a lot in the code of this lab, because this lab only involved glow script, not tracker. We have Newton's second law, which just talks about velocity and position update, that the net force is change in momentum over change in time. We also analyzed F net of parallel and perpendicular forces in this lab. Some other important equations are the fact that delta P, or change in momentum, is equal to F net times T, and delta P is equal to the perpendicular force plus the parallel force times T. So this is for coding part one. We have the initial conditions, which just has the G universal gravitational constant, the mass of the star, the delta T, and then we have Newton's second law coding, which is all the initial final velocities and positions that we needed to complete this part of the lab and to get results. Then we also have a picture of the code that I used to estimate the mass of the black hole, and also the arrows that will illustrate the parallel, perpendicular, and net force on the glow script computational model itself. So here I included a picture of the my lab or my star in mid trajectory. As you can see, the blue arrow is the parallel force, the orange arrow is the net force, and the magenta arrow is the perpendicular force. I included the mass of the black hole, average, and the net force. I also have the FNet parallel, which was 3.22 times 10 to the 27th, and FNet perpendicular, which was 8.67 times 10 to the 28th. So for this discussion, it was asking us basically just compare the parallel and perpendicular components and how that differs from rate of change and momentum and their parallel and perpendicular components. So there is no mathematical difference. We had to assume that the net forces of perpendicular and parallel are equal. We used this assumption to find the net force, which was then used to find the mass of the black hole, or the estimated amount, and rate of change can be calculated through observations. So this is coding part two. Once again, I included the initial conditions. This also included the mass that we found for the black hole in the other slide, which can be found there. And then just some other constants that we need to be made aware of. Then I included the FNet calculations that are occurring on the planet and the spacecraft separately, and then I included the initial conditions for the planet and spacecraft as well. Using all of this code, I was able to find the result, which was the initial velocity for the ship, which you can find on this slide. I also want to point out the potential errors real quick. Some of the errors include rounding values such as the universal gravitational constant and mass of the black hole for each iteration, and then just human error when typing in the code. And for part two specifically, not everything was accounted for when it came to part two. For instance, the best angle for takeoff from the planet. So for the discussion, one velocity vector that worked after some trial and error is listed on the slide. And I just want to thank you guys for watching my presentation.